Okay, I'm going to explain exercise 2.4 to you, but before that, first we must establish some of the basic foundation of that you need to know before we start. The first thing is that, as I mentioned to you in class, that the formula you learn in lower secondary school and in primary school, which is speed is equal to distance over time, is only applicable in certain situations. And in fact, the only applicable situation is when the velocity or speed is constant. So in most of the situation, you cannot use this formula. So the formula that you should be using, or the method you should be using, is actually the area under the speed or velocity time graph. And this method is applicable to all cases, whether it is constant speed or velocity, or whether it's accelerating or decelerating. Alright, so this is the formula that you should use henceforth, because you will make sure that you get the correct answer all the time. So let's go to exercise 2.4 now. For the first few questions, it's already very clear that the objects are all changing speed, so you cannot use that speed equal to distance over time. So in the first case, the rock is dropped with an initial speed of 20 meters per second. Thrown up with an initial speed of 20 meters per second. So this rock is actually undergoing free fall because there is no air resistance, ignoring air resistance. So we can say that the acceleration that the rock is experiencing is 10 meters per second. Alright, so since it's being thrown up, the motion of the rock is going to be in this way, with an initial velocity of 20 meters per second. Then finally, when you reach the highest point, the velocity is 0 meters per second. So throughout this whole journey, the acceleration is in the opposite direction of 10 meters per second square. So since we already know that we cannot use distance equal speed times time, we have to draw the area under the speed time graph. Right, so we draw in this way. Its initial velocity is 20, so you start here, and then as we know the gradient is a constant gradient, it will be a constant gradient coming down with gradient of minus 10, because this gradient represents the acceleration. Alright, so if this gradient is minus 10, then the time here has to be 2, because the rise over run of 20 divided by 2 will give you 10. Alright, so from here we establish how the diagram look like and the time and velocity. Okay, so what happened is, next is that to find the distance is just simply applying the area under the graph, which is half 2 times 20, which gives you 20 meters. So that's how you solve for the first question. Now for the second question, is a little bit more straightforward. There is again acceleration. So because of that, we again have to use the area under the graph for the second question. Okay. So it starts from 2 and then it goes all the way up to 12. Right, and then it does it in 5 seconds. So this will be the area that you need to consider. Okay, so if this is the area you need to consider, you can use trapezium rule, or you can use a rectangle and a triangle to solve for it. But to save time, I'll just use a trapezium rule. So the distance traveled will be half 2 plus 12 times 5, which gives you 7 times 5, which is 35 meters. Okay, nothing special about it, so the answer is C. Okay, so for the third question, so some of the things you need to know is that these two objects is falling through a rather short distance, 5 meters and 45 meters. So what you can assume is that the object is falling under free fall because of the short distance, we can assume the air resistance is negligible. So if it's falling under free fall, the acceleration that it experiences is a constant of 10 meter per second squared. Alright, so since it's accelerating, again we cannot find the distance using the normal way, but we have to draw the area under the graph. So for the 8 kg object, what happened is that this area under the graph will be 45 meters and the gradient will be 10. But there are two unknowns. The first unknown is T1, the second unknown is V1. Alright, in the same way for the smaller 2 kg object, you will have the same situation. Okay, but of course the area will be much smaller. And the two unknown will be T2 and V2. Alright. So because of these 4 unknowns, you need 4 equations to find the time taken, which is T2 minus T1. So the first unknown that you can use is actually this formula. Okay, A equal to V minus U over T. As we know, both the gradient is 10, alright. So what we get is we get 10 as the gradient, but the rise over run will be V1 over T1. The initial velocity is 0, so the rise over run will be V1 T1. So the first formula you have is V1 equal to 10 T1, and in the same way, you get 10 equal to V2 over T2, so V2 equal to 10 T2. So this is the first formula you get. The second formula is actually the area under the graph, so it's half V1 T1 is equal to 45. Now from the first formula you know that V1 is 10 T1, so you get this. Alright, you sub the first formula into the second formula. So from here, alright, I get 9 and T1 is equal to 3 seconds. In the same way, alright, half V2 T2 is equal to 5, so half 10 T2 square is equal to 5, T2 square is equal to 1, and T2 is equal to 1 seconds. So if they ask you for the time difference between the two, it will be T2 minus T1, which gives you 2 seconds. Right, so that's why you get B. Right, it's quite a hard question, but it's still doable. So let's move to the last question of this particular page. Alright, so in this case, this is an oil drop question where the path, where the interval is increasing for the distance traveled by the interval is increasing for the same time taken, because the time taken for the interval is always the same, but the distance is getting longer. So in the first part, it is accelerating. While in the second part, if we look carefully, this distance between these 2 points and these 2 points are the same. So actually this is constant speed. So the answer is B, where you accelerate then move at a constant speed. So at this point, I would like to draw your attention to something very interesting. Now, if it is oil drops that is producing these dots, right? Let's say you have these few dots here that's produced by oil drops from a car which is going from right to left, versus let's say you have a ticker tape, right, which is also moving from left to right. Let's say that the time interval for both is the same, alright, so they are moving to left to right, with the same time interval, with the same number of dots, right? We know that this is accelerating, as we can see from this first case. But the question to you is that, how about this second case? Do you think that in this second case it is accelerating, constant, or decelerating? So you may want to pause for a while to think about the answer. So what's the answer? In actual fact, the answer is it is decelerating. Why? Very simple. The key to answer this question is to ask yourself, which one is the first dot on the diagram? Now for the oil drops, the car have to start from here, right? And then it will move to here. So because of that, this is the first dot, and this is the last dot. So if this is the first dot, this is the last dot, the gap is getting bigger, so it's accelerating. Now for the ticker tape, what is happening is that it is actually a vehicle that is pulling the tape, alright, while the ticker timer is punching the hole. Alright, so if this is the starting position, alright, at the end position, the tape will have been pulled out, alright, further. So the starting position will have to be at the leftmost side of the tape, while the ending position will be at the right side. So with this kind of drawing, you can obviously see that the starting position this is the first dot. Alright, so this is the start dot or the first dot. Okay, so if this is start dot and then it is being pulled in this direction, so the gap is getting smaller until the last dot. So if the gap is getting smaller, it's decelerating. So you can see that the idea of ticker tape and oil drops are very different. Oil drop and ticker tape with the same shape will have an opposite effect. Alright, so this is the difference between the two. So take note, if you ever encounter this kind of question, be careful about what is supposed to be the answer. Alright.